To continue, it's an honor for me to introduce to Professor Liviu Ignat. You is one of the strongest mathematicians in the area applied mathematics and a partial differential equation today. Professor Ignat received his doctorate in 2006 in Spain under the guidance of Enrique Suazua. Likewise, his scientific production is high, having published 66 articles
Oh,
and has approximately 1,000 citations. He is professor in Institute of Mathematics Simeon Stolf of the Romanian Academy. On this occasion, Professor Ignat will give the talk entitled Asymptotic Behavior of Solution for Some Diffusion Problem on Metric Graph. Welcome, Dr. Ignat, and you can start.
okay. Thank you for your introduction. Maybe the number that you say that too high because we have two Ignat. Okay, maybe you join them, but anyway, I'll present a work that I did during some years with some collaborators. Ademir Pasotto from Rio, Julio Rossi from Buenos Aires, Cristi Casacu from Bucharest, and Angel San Antolin from Alicante. And I will try to, okay, I'll have a part, the first part to be very general, so I'll not try to be very technical. And probably in the last part, I'll have some more technical things, but at least in the first part, I'll try to, okay, to explain the main ideas and as easy I can try to do it, okay? So I'll have a part about classical diffusion and how you can obtain the asymptotic behavior. Asymptotic behavior means when time goes to infinity. I'll present the result, maybe even if it's easier to obtain about how to obtain asymptotics for heat equation on graphs. And after that, I will enter in a nonlinear problem on graphs. And okay, if I have time, I will enter in the non-local part. If not, I'll stop at the first three parts. So about classical diffusion. So the easy problem is that when you start to enter in this subject, it's okay, you have the heat equation, think on the real line. You can have also multi-D cases, but think on the real line. If you have integral initial data, you are able to write your solution as a convolution between the heat kernel with the initial data. So in fact, you have a clear way to represent your solutions. And if you look to the decay of the solutions, for example, here, if you take p equal to 1 and q infinity, you have that the solution decays uniformly as Tn minus 1 over 2. Okay? So your solution, if you start with some integrable initial data, your solution will decay in time. And you know that you have a decay rate. Okay, probably that is not the optimal one, but you can think maybe you can do better. But what it's possible to prove is that in fact that Tn minus 1/2 it's optimal in the class of integral initial data. Now, what you can do when you don't have a kernel, so if the kernel is not explicit as here when you have the Gaussian, so think that maybe you have some more complicated problem where you are not able to use Fourier transform, but you have an operator A, and you want to see what's happened with the solution. So you want to analyze the problem ut is A of u, and you can write many properties of your equation in terms of the bilinear form AUV, which is minus A of uv. If you think of the Laplacian, this is the gradient u gradient v. And of course, you have many properties that you can characterize in terms of the bilinear form. For example, if initial data is positive, the solution is positive. If the initial data is bounded, when the solution remains bounded. But what is more important for us is what's called ultra-contractivity, which means that you want to see if you have an L1, L2 property as before. So if Q is 2, you have L1, L2. If you have Q infinity, you have L1, L infinity. In fact, if you have L1, L2, you automatically will have L2, L infinity. And since you have L1, L2, L2 infinity, you will have L1, L infinity. So it's enough, for example, to study L1, L2 property. And that ultra-contractivity is related with many things like this logarithm solution inequality, Nash inequalities, and so on. So now, for example, if you want to obtain that your solution has an L1, L2 decay as Tn minus, okay, that's just number. You can put here beta if you don't like alpha over 4. So that is equivalent to if what is called a Nash inequality. It means that you want to control the L2 norm of any function u in terms of the bilinear form associated with the operator and the L1 norm. Of course, you have some powers here which are given by homogeneity. And this inequality here, it's equivalent with this Nash inequality. Of course, now, if you look to the literature, you discover that, okay, you can ask that this property to hold for any positive t, or you can ask this property to hold for any small t, or you can ask the property to hold for any t greater than t0, okay? Or you may ask initial data not to be only L1, but to be to L infinity and so on. So those L1, L2 decays you can state in many ways if you want for any t or for any for any sufficiently large t0. Anyway, there are books on that. For example, the most recent one is one of Havath, who collects many results from previous paper of Davis, Carlin, Struck, Varopoulos, Coulon, and so on. Okay, so you have a book where you can find any property that you want in terms of L1, L2 decay for linear problems. Now, coming back to my first question, is if that Tn minus 1/2 was optimal. So think that when you try to, when you have sine of x, so sine of x, you say, okay, sine of x close to 0 is less than x. Okay, perfect. But in fact, you can say more. It's not only that it's less than x, but close to 0, sine of x is like x minus something or plus something, which is O or some O of x to the power 3. So exactly the same you can say in the case of the asymptotic behavior when t goes to infinity. So of course, first you say, okay, my solution is bounded. Okay, perfect. But you can try to see if you can say more. Okay, it's bounded, but when time goes to infinity, that solution is closer and closer to some profile. So the answer for the heat equation is true. So you have, if you have initial data with mass m, your solution is closer and closer to a Gaussian profile. Of course, you have rates. So if you put here infinity, in fact, you have that t1 at 1/2 u of t minus mg of t in L infinity goes to 0. It means that the difference goes to 0 faster than t at 1 minus 1/2. Okay, so each one decay as Tn minus 1/2, but the difference between them decay faster. Okay, if you want a proof, okay, this is all is linear. Here you have a explicit representation of solutions. You can play a little bit here with a Taylor expansion, and you have the right decay. Now, if you want more terms, there are some tricks by Dwanico as well in the 90s that they allow for linear problems, and when you know very well the kernel, to obtain more terms. It's just the composition of the initial data in some base of Dirac deltas. Now, okay, that was in the case when all you have is explicit. Now, what happens when you don't have explicit things? So, well, before entering something complicated, I'll give an example how to use scaling arguments to obtain, again, the same property as here, okay? So this property, if you look carefully at p equal to 1, it means that u of t goes to mg of t in L1. So you don't see that power of t. So the idea is to try to see if u of t goes to some profile in L1. Now, what's happened with the scaling? So the scaling argument means that you have a solution u of your equation, and you introduce a change of variables that in that case is somehow the scaling that leads invariant to the equation. So for example, that u of lambda squared t lambda x. And what is important is that if you want to prove that u of t goes to some mg of t when times goes to infinity in L1, it is equivalent to say that the new family u lambda at time 1, for example, converts to a profile f of m, which is exactly the Gaussian at time 1, times something, in L1 when lambda goes to infinity. So, in fact, you only have to prove that this family U lambda, defined as a scaling, and rescaling the solution, converts to something at time one. Now, how it works now? Okay, you have that method has been introduced by Vasquez Camin in the, I think, 80s, and you have to rescale the equation. Of course, in a nonlinear problem or in a more complicated problem, you may have difficulties at this stage that I explain now. So you may have problem to write. If you have strange operators, non-local things, you may have problem to write, or it's not too easy sometimes to write the equation for U lambda. Sometimes it's difficult to obtain compactness of the family U lambda. Think that you have to prove that U lambda time one converts to something, but to prove that converts to something, first you need compactness. So somehow you have to prove that U lambda has good compactness properties. And once you obtain that U lambda converges up to a subsequence to something, you have to identify that something, okay? So that something will be a solution, for example, here for the heat equation, will be a solution of the exactly the same heat equation, but with initial data Dirac delta. And here, depending by the problem, you may have a problem with the uniqueness of the limit profile. Of course, you know that you have uniqueness for heat equation with Dirac initial data under some very mild condition and so on, but you may have difficult, or you may have a strange limit equations where you may not be able to prove uniqueness of your limit solution. And we have example that we are, okay, in other problems, we almost did the paper up to the final step where we don't know how to prove uniqueness. Now, okay, the method is good for nonlinear problem. It works very well for the first time, the asymptotic expansion of the solution. As far as I know, I never seen applied to obtain more terms in the asymptotic expansion of U. So think that you may think that you may obtain more terms in the asymptotic expansion of U, but at least as far as I know, it has been done only for the first term, not for the second or third term, the asymptotic expansion. So that was heat equation on the real life. Now I'll go to a heat equation on a graph now. Okay, so I'm trying to adapt the techniques that we have before to some equation on a graph. Now it's important to understand what's happened, what is a heat equation on the tree. For example, think that you have a graph. For me, a graph, you have edges, and I write the equation on edges, and I only use the vertices, to couple the equations. So if you have a tree line connected at the point, I write an equation on each of the three lines, and at the common point, I'll couple somehow the three equations. So that is a heat equation on a graph. Maybe at this point it will be better to make a picture, but okay, I'll see if I have to do a picture on that. So what we assume is that on each edge, okay, maybe I will share also the screen. Maybe it's better to share the screen, the whole screen. And to try to give you an idea of what kind of equation I'm trying to solve. So think, for example, that you have some lines as here. So each one you parameterize with minus infinity 0 or 0 infinity. And on each one you write an equation, ut minus uxx equal to 0. Here so this is u1. Here I have u2x, ut2 minus uxx equal to 0, and so on. So I have n edge incoming edge and m outgoing edge. And here in the middle, I have to couple somehow. What I said before was that Kirchhoff type coupling. It means that at common point, I assume continuity. So each edge that entry at 0 minus, it's uj at 0 plus. And the other condition that it's appearing that Kirchhoff type coupling is means that the sum of derivatives from the left it's exactly the sum of the derivative from the right. Okay? So that is the type of coupling that I'm thinking of. Okay, there are in the literature more different couplings, but for me, that will be the easiest model, and I'll work with that easy model. Now I'll go again to my slides. Okay, so think that you have many equations on some edges, many equations on other edges, and you couple them. Okay, your graph has a common or a compact part, which is made of finite edges. I denoted here gamma f, and some edges which are infinite edges. Okay, and I want to solve the heat equation on those edges. I assume that I have at least one or two infinite edges in order to have an infinite part, and not we have only a compact part. Now, what we proved was that if you have we proved a similar result as in the case of the heat equation on the real line. So think that you have a finite part of the graph and an infinite part of the graph. And what we proved was that your solution is closer to a Gaussian profile. A Gaussian profile in this case is just on the infinite line, you put some Gaussian profiles. Of course, you have to normalize because the mass is not exactly, somehow the mass is spread on the infinite lines, but it's uniformly spread on the infinite lines. And on the compact part, we have in fact a faster decay than on the infinite part of the graph. So we were able to prove that there are some profiles, limit profiles for the solution of the heat equation on the graph. Now, of course, this is done, okay, that heat equation on the graph is just, let's say, a baby model, and you can try to complicate it more and more. Okay, in the case of the heat equation on the graph with that Kirchhoff coupling, what we have is that, okay, we have mass conservation, and that can be seen the type of coupling that you put. We have a decay of the solution, and in that case, in order to prove the decay of the solution, since not always you are able to obtain an explicit kernel there, even there are some combinatorial formulas to obtain the kernel, maybe the easiest way to obtain the decay is to write the equation exactly as in that ut is a of u, and try to use Nash inequalities. Of course, in that case, for graphs, there are some previous results of Delio Mugnolo and Hessler, who proved that even for the graphs, there are some kind of Nash inequalities. Okay, so it's exactly as in the 1D case. So even for the heat equation on the graph, we recover all the properties that we have from before. Now, how we did it? Okay, that is just to learn the method, how to apply scaling method on graphs and to apply to more complicated problems. So in that case, for sure, you can do it in other ways. Since you have a linear problem, your graph is not so complicated. But we like to understand the method. Okay, so you have a graph which have a finite part and an infinite, some infinite lines. Now you do a scale. So you define u lambda x is lambda u of lambda x. This is exactly the scale that you do in the real life. The problem is that the new function u lambda is not defined on exactly the strange structure gamma. So you have a graph gamma who has two parts, gamma f and gamma infinity. When you define the function u lambda, think that each segment, each edge of the graph is parameterized with 0L. If you have a function defined on 0L, then your function u lambda should be defined on the interval 0L over lambda. So the new graph gamma lambda shrink somehow with lambda. So the compact part is shrinking and the infinite part remains invariant. So under that transform, the graph gamma is converted in a graph where only one part is invariant and the other one is not. Okay, and that gamma lambda f, the finite part, collapses to 1 point. Now, okay, you do your four-step method. You rescale the equation. You have that u lambda, it's again the solution of a heat equation, but on a new graph, gamma lambda. And you have also to rescale the initial data. And all your u lambda satisfies the same inherent the same properties of your initial inherent all the estimates that you have from U, and okay, you have also to prove some tail control, but those estimates allow you to obtain that the family lambda converges to something. So you get compactness. Now, if you have compactness, you have that U lambda converges to some U. Okay, that is converged in C1 log. Okay, now you have a tail control, so you pass from a L1 convergence to an L1 on the infinite lines. Now you want to obtain the limit equation from the profile U. What's happened is that when you write the weak formulation for your equation on the whole graph gamma lambda, so you have a gamma lambda graph, you write your weak formulation on gamma lambda, and when you pass to the limit, you'll not see the part gamma, the finite part of graph gamma. You will only see the limit, the invariant part of the graph. So that finite part, when we rescale, shrink and disappear in the limit. What appears is that you have a heat equation on the new graph, which is only the infinite part of the graph, with some kind of Dirac initial data time equal to 0. Now, of course, you have to prove uniqueness of these solutions. And once you have uniqueness, you can identify the profiles are exactly the Gaussians multiplied by 2m over n, when m is the mass of the initial data and n is the number of edges of gamma infinity. And as a conclusion, you obtain that U lambda time 1 converts to that profile U, okay, at time 1. And on the final part of the graph, you have to work a little bit more, but in principle, once you have once you get the convergence on the infinite part of the graph, you will obtain also on the final part of the graph. Now, that was for the heat equation on a graph. And that problem was a linear problem. In fact, all I presented until now was only to understand the main ideas that stay behind the proof how to obtain asymptotics for equation on the real line or on the graphs. Now, I will give you a more complicated problem, a nonlinear problem, where you want to obtain the asymptotic profile of the solution. So what we did, that it's a paper published 2 years ago, and think that you have a convection diffusion equation on some lines that they are joining at the point x equal to 0. So I think that you have Burger's equation. Even Burger's equation is more complicated from the asymptotic point of view than the other ones. So think that you have a Burger equation on negative lines. You have E negative lines, half lines, and you have M positive half lines. And you couple the equation in that way. You have assume continuity at the common vertex, and you have a mass conservation property, a flux coupling condition that allow you to control what's happened with the mass. Now, under that flux condition, what you have is that the mass is almost conserved. Think that, for example, you have f of 0 to be 0, and in this formula, you have that the mass is conserved. Or if you have, or f of 0 is not 0, but you have n and n. The number of entries is equal to the number of outgoing edges. Now, you have to take care when you analyze all posedness of this problem, because if you try to use semigroups, so okay, the first paper that I know on that well, posedness was something by Coclite Garavello on something with traffic roads, okay, model for traffic flows. And when you use that formulation, that in principle is a formulation that you have in the case of the real lines, the two formulations are the same because the semigroup commutes with the derivatives. Here, the semigroup does not commute with the derivatives. And you have to take care when you pass from the first formulation to the second one, because here they are not really equal, okay? So in that case, when you have to apply semigroup methods for nonlinear problems on, let's say, networks of graphs, you have to take care how you apply the semigroup method, because if you have derivative in general, the derivative does not commute with the semigroup. This is because you have the linear problem, you have some coupling conditions, and when you look to the derivative of ui and uj, they are not coupling in the same way as u. So you have different coupling conditions for the derivatives. So you have to take care, because when you make when you try to commute the derivative with the same group. Okay, there is a way to apply in a careful way the semigroup method for graph. I remember I saw a paper by Kaisa Marie and Paul on KDV equation, where they really take care how to obtain the existential solution and well-posed by semigroup method. Otherwise, if you don't like to use semigroup and you think that maybe it's more complicated to use a semigroup, you can use an iterative method. You write the weak form of your equation and you can try to do an iterative method that obtains the well-posed. Now, what we obtain, we have a global well-posedness result, but that depends on the sign of f and on n and m. So on the real line, think that you have f of x to be u to the power, that is our model nonlinearity, s to the power q minus 1s, okay? When q is greater than 1. So in the real line, you don't see any difference between n and m. So n and m are equal with 1, and you don't see any difference at this level. So n equal to m, it means that all this line disappear because it's automatically satisfied. Okay, when you have n and m edges, you have to take care, because if you want to control your solution and you need energy estimate, you need a sign condition between the nonlinearity and the n and m. So you have, for example, if f is plus minus sq minus 1s, you have to assume that n is less than m, for example, in the case with plus, okay? And for even nonlinearities is not covered, because you don't know how to treat exactly for changing initial data, okay? Changing sign initial data. You know, to prove, okay, for non-negative, non-positive, but not for general changing sign solution, because you have a problem to control some norms. Okay, why this happens? So if you take your favorite idea here, you take a convex function and you try to have an energy estimate. Usually when you are on the real line, you don't see this last term. So if you are on the real line, you'll not see that term that comes from x equal to 0. And for example, if you take rho to be a square, so you want an energy estimate, you have, okay, that the time derivative of L to no plus some gradient, it's equal with this quantity here. So if you want a global well-posedness, you have to be sure that this quantity is negative. So this quantity will be negative if n is less than m. Otherwise, if this is positive, you are not able to prove that your solution exists globally in time. So you need a sign condition in terms of n and m. Okay, good. Okay, so here if u is positive, this quantity is positive. If u is negative, this quantity is negative. No, this quantity is positive again. So you need that n should be less than m in order to guarantee that you have global solution. Now, as a corollary, we obtain, for example, that if initial data are bounded from below, then the solution remain bounded from below. And if initial data is upper from above, also you have a bounded solution. But that depends on the existence of some constants that verify that condition that n minus m f of m is positive or negative. Okay, but that is a corollary of the previous result. Okay, so if you want to obtain bounded solutions, you have to take care also about n and m, and that is exactly that condition on limit and lib sup of f. Okay? That condition guarantees that you have that your solution remain bounded forever. Now, as a remark, okay, constant solutions are, okay, so constant function are solution if and only if n minus m f of c is 0. So that cases where the constant solutions are not solutions, okay? So constant functions are not solution, which is a little bit strange compared with what happened in the real life, but that is because we may have we are not on the real line, so here we may have strange solutions. And if n minus mf of 0 is 0, then the solution remains non-negative, the initial is negative, and the L1 does not increase. So you can characterize some of your properties that you want. For example, L1 estimates or positive solution in terms of n minus m f of something. Okay, that was from the point of view of existence, but now if you want to analyze, to look to the asymptotic behavior, what you'll see is the following one. Okay, so we have a thing that we have in the case, we have that nonlinearity. You have a sign s q minus 1s with q greater than 2. Okay, A is such that n minus m, A is positive, so we have global solution for L1 initial data. So we have a mass conservation property in this case, because f of 0 is 0. And what we are able to prove is that when Q is, okay, we are on a star-shaped structure. So here I'm not talking about finite part of the graph, infinite part of the graph. So here I only have an infinite, I have only infinite lines. So I have an equation on n plus m lines, n on negative and n on positive. And what we are able to prove is that in this case, when Q is greater than 2, the solution behaves as a linear heat equation on the graph, and the limit profiles are those given by the Gaussian profile. Now, what's happened with Q equal to 2? So Q equal to 2 is tricky, because in this case, assume that, for example, you have non-negative initial data, then you have some profiles which are Burgers profiles, but those Burgers profiles are more difficult to write because those in fact are function has some properties exactly as the Burger equation of the half line, with the difference that here the profiles depend by some parameters that depend by n, and m. And this constant is obtained as a unique solution in the interval, this interval of this nonlinear equation. So I will explain you later how we obtain those profiles, because here it's a difficult part of our paper. And there are some questions. For example, okay, what we obtain is that when Q is strictly greater than 2, the long time behavior is obtained by scaling, and it's exactly as in the case of the heat equation. So it's like a heat equation on the graph. When Q is 2 is like a Burgers equation, but we have no idea what's happening when Q is less than 2. So when Q is less than 2, it's exactly on the real line, or this is a hyperbolic regime. In that case, you need to assume some, okay, you need to prove some Olemic estimates, which we have no idea how to prove it. And what is difficult in our case when Q is equal to 2 is to obtain the uniqueness of the limit profile. So I'll give, now I have to, so I have 10 minutes more? Okay, so I will try to give some idea how to obtain the limit profile. So in the limit equation in the case Q greater than 2, when after scaling, is a solution of a heat equation on a graph. So you have heat equation on each line, coupling with the Kirchhoff coupling, that you have continuity, and the sum of the derivatives from the left and from the right are equal. But the initial data is taken in the sense of Dirac measure. So this is exactly this line saying somehow that your solution U is like a Dirac delta as a common vertex. So your solution limit profile satisfy this equation here, and you have to prove uniqueness. Okay, we have uniqueness from your previous result. So here we have a limit profile that you know exactly, and we know that it's unique. Now, what's happened if you try to do, you can put the same question, okay, so here this is a limit profile that you obtain when q is greater than 2. This is a linear problem that you may ask, I can consider the same problem, so I can consider nonlinear problems on each edge. I have a coupling condition that guarantees that the mass is conserved, and I take initial data, a Dirac delta. Can we prove that we have uniqueness? And that for us was a difficult question that we were able to do it only in the case when Q is 2 and we have non-negative, we have positive solutions. So in general, we don't know how to prove uniqueness of this type of problems. We know, for example, in the case Q equal to 2, how to treat it. Because somehow we have to use an adaptive Hopf transform to obtain, to take an, let's say, take a better idea of how the solution are. Now, think that you have this equation on edges. So somehow this equation, you have n equation on negative lines and m equation on the positive lines. So somehow the equation is symmetric on the negative components and positive on the positive component. So assuming that you have proved that, okay, even that is not an easy trick to prove that you have all the solutions from the left are equal and all the solutions from the right are equal. In that case, the equation is reduced to something on the real line where you have a convection diffusion equation on the left and on the right. You have a continuity condition here, but you have a strange nonlinear coupling at 0. So it's if n is equal to m, you'll obtain something as in the case of the real line, so you have no problem. But when n is not m, you have something very, very strange here. It's something saying that you have a convection diffusion equation with some strange term at 0, such that the initial data satisfies the fact that n1f minus plus m1f plus is 0. It's m delta 0 in the sense of measures. It means that satisfies this condition here. Now, as I said, when n is equal to m, there are results for non-negative or non-positive solutions. There are some papers, if you don't have diffusion, there is Lupierre. After that, there are papers of Escobedo Vasquez-Boisois and Anna Carpio, for example. But the difficulty appears when m is different from n. And the big difficulty, in order to apply the previous method of those authors, is that if u is a solution of your equation, the translation does not solve the same problem. So the trick that you use in the case of the real line is somehow you take your solution, you take a translation and try to compare what's happened with you and the translation of you. And maybe you are able to compare somehow, and that will give you uniqueness of your solution. What we did in this case, we proved that we have, so I have until 30 or 40. Okay, so I assume that I have more minutes. Okay,
Yeah,
so.
you have 1 or 2 minutes, yes, I think.
Okay, I'll try to finish. Okay, so the idea that we used to prove uniqueness in this case was to use an adaptive Hopf transform that reduce. So usually in Hopf transform, n is equal to 1, so you choose exactly the primitive of u, and the primitive satisfy a heat equation with a heavy side initial data. So initial data is 1 and this power here, this number here. But what we have in our case, since n is different from m, you have a nonlinear coupling condition at 0. So you have a heat equation on the left, on the right, and we have some strange coupling condition and x equal to 0. And in that case, after some, we solve some Neumann problems, some heat equation with Neumann condition at x equal to 0, and we have some integral equation for the restriction of W on the left and on the right for the solution of the heat equation. And finally, after some change of variable, some clever notations, we reduce the equation to the following one. So we have an integral operator of this form. So this operator, when applied to constants, you obtain constants, and you have to solve so somehow your heat equation on the left, for example, multiply by some numbers, satisfy is a solution of this crazy equation. This is an integral equation, a nonlinear integral equation, and you have to prove that the unique bounded solution is a constant. It's exactly the constant that you want from before that depends by n and m and n, m, and m, capital M, and you have to solve this nonlinear problem. Okay, nonlinear integral problem. I will stop here. I will go skip directly to I'll skip the no-local part on the graph. Okay, what we can do more. Okay, you can try to do different couplings, not only Kirchhoff, but there are delta and delta prime couplings, which, okay, sometimes are more difficult. And for example, other problem is to incorporate transport terms. So think that you have a heat equation with some transport term on the left and on the right. It's like having an equation where you have a transport term with sigma here that change from two values, from 1 to 2. And you want to know what is asymptotic behavior. The equation maybe behaves as when you have 1 on the left on the half plane and 2 on the other half plane, but maybe you have something in the middle. So we have something, but we are not, we don't know exactly, okay. We have something, but not completely. Okay, you may try various things like trying non-local, non-linear convection diffusion problems. There are some, you can try to use some fractional Laplacian instead of local operators and so on. And okay, I want to stop here.
Thank you so much, Dr. Ignat, for your excellent presentation. Do you have any question or commentary?
I have one question, please. Yes.
Yes.
Thank you. Yes,
Johnny?
thank you, Livio, for your talk. I liked it a lot. And I have a curiosity because in one case, I think that when Q was greater than R2, or in one particular case, you mentioned that maybe the Oleinik inequalities could be useful. No?
Yes, but the problem is how to obtain it.
Eh? Sorry?
The problem is to obtain it.
Yes,
How to
because
obtain
I
it.
am not
Okay,
familiarized with them.
on the
And
real line, you have to use it. I have no idea if you don't have it, how you obtain that asymptotic behavior. The problem is how to obtain such estimate when you are in Q, when you are with Q less than 2, but you couple equation. You are not on the real line. You have some equation on the left and then some equation on the right.
okay.
So
Because
if you give me a proof of that inequality or something similar, I can give you an estimate for the long time behavior of the solution. But we have no idea how to obtain it.
Okay, thank you. It's a pleasure to see you here because I have read articles by you many times. So thank you, Livio.
But you are in Bilbao?
Yes, with
Oh.
Jonasier Bartena. I have worked.
Okay.
with him.
Okay.
Yes, yes. Thank
Thank you, Johnny. Any question? Other question or commentary? Any question? Or I have a curiosity. You also have a no-local diffusion result in graph?
Yes, we have. I skipped it because I was lack of time. So, okay, our baby model, okay, on the real line is that Jota of Julio kernel. So is that kernel that Julio likes a lot. So I started to work with Julio many, many years ago, and at some point we decided to do the same equation on a graph. So we have a non-local equation on a graph, and of course, in that case, we also had some result on asymptotic behavior of the solution, but only for the linear problem.
Thank you, Professor Ignat. Other question? Any question? Well, if there are no more questions, thank you again, Dr. Ignat, for your amazing
Thank you for
talk,
the
and
invitation.
see you in other opportunity.
Okay.